Okay, so hi everyone. So it's my pleasure to introduce Bradley Kavanagh from the Institute of Physics of Cantabria in Santander. So Bradley and I go a few years back. We shared a PhD supervisor, Anne Green, who you may remember from a seminar from a few weeks ago. So Bradley was a few years ahead of me in Nottingham, and then he went to do a postdoc in Paris. I forget which of the many acronyms you were actually affiliated with, but there are several.
Too many.
And then he was in Grappa for a few years before moving to his current position. So Bradley's done a lot of work on lots of things related to dark matter, but he's going to talk to us today about primordial black holes specifically. So take it away, Bradley.
Thank you very much. Thank you very much for the invitation. Thanks for the nice introduction, Kieran. So, as Kieran says, I'm going to talk today about primordial black holes, but I'm going to start this talk the way all good astroparticle physics talks should start, and that is with werewolves. Okay, so werewolves, as I'm sure a lot of people know, are creatures of mythology and legend. They are humans who can shapeshift into the shape of a wolf, okay, usually when there's a full moon, and they're very, very hard to kill, okay. This, I promise, will be relevant at some point during the talk. So now we turn to what you actually should start every good astroparticle physics talk with, which is dark matter. Okay, so we know that there's dark matter in the universe, and we know this kind of from observations on all scales. Okay, so if we start off on CMB scales, looking cosmologically, we know that the shape of the fluctuations in the CMB tell us that we need this extra component of missing matter to seed structure formation. We can imagine sort of zooming in on one of these patches to look at filaments of the universe and look at clusters of galaxies. Okay, and the clusters of galaxies have a huge mass to light ratio. So the amount of mass that they have, you can infer from gravitational lensing, studies of X-ray emission, is much, much more than the light that you can observe. Okay, and so on these large scales, we know that we need dark matter, and we can zoom in one more time to individual galaxies in these clusters. And the rotation of these galaxies is essentially flat. The rotational velocity is flat out to large radii, which tells us that there's some missing component of mass, which isn't accounted for by the stars or the gas in the galaxy, which is required to keep this galaxy in rotation out to large distances. Okay, so we have a lot of evidence that these that dark matter exists. The question is, what is dark matter? Okay, and how do we find it? And one possibility for finding dark matter is called indirect detection. And the idea here is that you look for the products of dark matter annihilations and interactions, and dark matter can annihilate, for example, into gamma rays or charged particles. And here in the bottom left, I'm showing a compilation from a few years ago from a review of constraints on the cross section for this annihilation process as a function of the mass of the dark matter particle. And each of these curves is just a different constraint from a different experiment. Okay, and as you observe different parts of the sky, and as you observe for longer and longer and more precisely, you can improve these constraints on the cross section for this process by looking at dense regions of the sky where you expect there to be a lot of dark matter and looking for the products of this annihilation. Okay, and we can kind of rephrase this slightly. So instead of just sort of looking generically for a specific value of the cross section, we can look at specific models. Okay, so generally people talk about so-called weakly interacting massive particles when they talk about at least these kinds of searches. And one particular model that you can think about is here, this is the MSSM, the minimal supersymmetric standard model, which is an extension of the standard model, which permits a new dark matter particle which you can look for. Okay, and so these two solid curves are constraints from indirect detection from the Fermi-Lat telescope, okay, constraining this annihilation cross-section. And this sort of bounded region is the best fit region for this particular model, okay, which satisfies these indirect detection constraints, other constraints, for example, from direct detection, and also the relic density constraint. Okay, so having this model provide all of the abundance of dark matter. Okay, the frustrating thing, I think, that some people feel, a lot of people feel maybe, is that as you improve these constraints, as these lines go down, these contours basically go down with them. Okay, it's very hard to find a bit of this parameter space where you can't have dark matter. Okay, as you bring these lines down, you just chop off another piece of this parameter space. The best fit point maybe moves around a bit, but it's very hard to reach far enough down to exclude all of this. And so a lot of people, feel that the WIMP model is hard to get rid of and hard to falsify, but also in some ways hard to detect, okay, because you don't know where in this plane the dark matter lies. Okay, and this is one reason that people are becoming interested in gravitational waves, looking for new ways to search for dark matter. Okay, gravitational waves are waves in space-time generated by a changing mass quadrupole moment. So anytime you have something heavy moving around, generally you need two things, but not necessarily. But you can have a pair of black holes, a pair of neutron stars, creating gravitational waves. And so what we did last year was try and kind of survey the landscape of possible ways that you could use gravitational waves to probe dark matter, particular dark matter candidates and models. And this sort of summary plot here shows you that you can use gravitational waves to constrain dark matter over a huge range of possible masses. Okay, I've sort of indicatively put indirect detection here, but standard searches like direct detection, indirect detection would live somewhere around here. And gravitational waves opens up a whole number of new ways to look for dark matter. Okay, and as we said before, I'm going to focus on primordial black holes. Okay, which for the moment at least looks like it really limits you to this narrow range of dark matter masses, where these primordial black holes are really solar mass, heavy enough to be detected in current experiments. So the overview then is that I'm going to talk first about the mergers of primordial black holes, some of the work that we did looking at deriving some constraints on the fraction of primordial black holes in the universe from observations of black hole mergers. And then I'm going to talk about what you can say about dark matter if you ever detect primordial black holes, which is very interesting. And then at the end, I'll kind of change style a little bit maybe and talk a little bit about what's been happening in the field in the past 6 months or so. There have been lots of new results, lots of some results seeming to contradict each other. So I'll talk a little bit about that, and we can see what's interesting and see what the next steps are for moving forwards. Okay, so let's take a step back. I think Anne Green probably told you plenty about primordial black holes, so I'll just take a few minutes just to go over that. So primordial black holes are black holes which could have formed in the early universe, so very, very early on before matter-radiation equality, and you need large overdensities to form these primordial black holes. But if you do form a primordial black hole, then its mass is roughly correlated with the mass inside the cosmological horizon at the time of formation. Okay, and depending on the redshift of formation, depending on the scale of these fluctuations, you can get, in principle, primordial black holes over a wide range of masses. So all the way from dwarf galaxy-ish mass scales, solar mass, black holes, planet and Earth and Moon size, down towards asteroids and comets. Okay, anything below this is likely to have evaporated by the present day. So doesn't make for a very good dark matter candidate, unfortunately. So you might ask how you produce these primordial black holes, considering that we know from measurements of the CMB with Planck that fluctuations in the early universe, primordial fluctuations, have to be small. Okay, and so this is the primordial power spectrum, and this sort of allowed region by Planck is this very thin white band which you can't even see. Okay, so the shaded regions are ruled out, and so anything really, the fluctuations need to be right along this line, but that's on very large scales. Okay, so that's on scales concerning clusters and much larger. Whereas if you're thinking about on smaller scales, the power spectrum is much less constrained. Okay, to reach the kind of fluctuations that you need to produce primordial black holes, you need to get somewhere up to this 10 to the minus 2 level of primordial fluctuations. And actually, on these small scales, thinking about solar mass or asteroid mass primordial black holes, there are very few constraints. Okay, and so you have to come up with a way of producing these large fluctuations, or some other mechanisms such as collapse from cosmic strings. But at the moment, there's no good observational reason that you couldn't have these large fluctuations to produce primordial black holes. And so the approach is then to turn it around and say, well, it's possible that these things could have formed. So how would we observe them today, or how would we observe their influence on the universe? Okay, so along with Anne Green, we put together this review and some associated code with all the bounds on primordial black holes, or compiling as many as we could manage to find. And in some cases, the papers were coming out faster than we could write. But this is the kind of plot that you get if you try and overplot all of the primordial black hole bounds. And so if I clean that up a little bit and try and divide these into categories, down here at very low masses, sort of sub-asteroid mass, you're constrained by the fact that these primordial black holes would evaporate. The products of those evaporations you would be able to see either today, or they would influence the structure of the CMB early on. In the middle here, if you have something which is sort of stellar or planet mass, then these things would act as microlenses, and you would be able to look at microlensing surveys and see the influence there. On very large scales, you would start to disrupt the dynamics of dwarf galaxies, for example, and so that's constrained. You can also accrete baryons, and so you would either emit radiation today. The baryons accreting would heat up and be sources of, for example, X-rays, which you could see. And then here in this range, sort of subsolar up to 100 or 1,000 solar mass, is gravitational waves. Okay, and this region has become really of incredible interest in the last 5 years or so, and that's because of the observation of black hole mergers by LIGO and Virgo. Okay, so LIGO and Virgo are interferometers looking for these merging black hole events, and the first event was this one, GW 150914, Yeah, that looks like the smallest number, so that was definitely the earliest one. Okay, and it was a merger of two roughly solar mass black holes, sorry, roughly 30 solar mass black holes. And so people started raising the question, could these 30 solar mass black holes be primordial in origin? Okay. Of course, the landscape has changed dramatically. This particular plot showing the masses of the initial black holes and then the final black holes of all the observed mergers. This graphic was produced in 2018, and then, you know, writing this talk and writing talks before it, I've had to update because in 2019 the number of candidate merger events grew drastically, and then it's still evolving. We've now seen very, very heavy merging black holes. Okay, so this is a field which is very active, both on the observational side and also on the theoretical side. And so what we can do is we can say if LIGO observes a number of merging black holes, then we can perhaps hope to constrain the fraction of primordial black holes, the fraction of the dark matter in the universe, in the form of primordial black holes in this particular mass range where LIGO and Virgo are sensitive. And to do that, we need to know, given some number of black holes, given some fraction in the early universe, what is their merger rate today? How often should we see them merging? Okay, and this kind of, there are two ways to think about it. There are two kind of channels, at least on first glance, there are two channels by which you can form these black hole binaries, which might merge today. One of them is, the first one is in the late universe. So the idea here is that you would have primordial black holes, which are single black holes until sometime in the late universe when they start to be they start to gather into bound structures like galaxies. At that point, they're in dense enough environments that they might happen to find other primordial black holes. And if they have a close encounter, they can emit gravitational waves to form a binary. Okay, the other possibility is actually if you just have a random scattering of primordial black holes in the very early universe, two of them might be close enough together so that as the universe expands during the radiation era, those two primordial black holes find that they will start to infall towards each other. They'll decouple from the Hubble flow and form a binary. Okay. And so there were a couple of papers out not long after the 2015 observation of primordial black hole mergers, you know, proposing these two channels. I mean, some of this had been discussed before, but it was really brought to the front again. And it turns out that when you do the calculation, this channel here, this early universe binary channel, is dominant. Okay, and the reason why this should produce so many binaries, that's not looking good. Anyway, so the reason that this should produce so many binaries is simply that the condition for forming a binary in the early universe is that the relative density of a pair of primordial black holes should in some sense equal the background radiation density at or before matter radiation equality. Okay, if one primordial black hole can see the overdensity from another primordial black hole, then they should start to infall towards each other. Okay, but if the fraction of primordial black holes, if all of the dark matter is in the form of primordial black holes, then almost by definition, when you reach matter radiation equality, then the local density due to primordial black holes comes to dominate. Okay, and so these things have to start infalling towards each other and forming binaries and clustering and things like that. Okay, so you should form a huge number of binaries in the early universe if this fraction is close to 1. Okay, so the image that you should have in your head, the picture, is that you have a pair of primordial black holes which happen to be near each other in the early universe at some high redshift. At early times, they're moving away from each other, getting further and further apart, but at the same time, the universe is becoming more and more dilute due to the expansion. And so at some point, they start to feel the mutual attraction and they infall towards each other. Okay, and they'll form probably a relatively tight but highly eccentric binary, and so they'll start orbiting. Okay, and they have these close passages. They'll swing out, and they'll undergo these this eccentric orbital motion. Okay, and then over a huge amount of time, over the whole age of the universe, this binary will emit gravitational waves, and finally shrink, and then today, or sometime near today, will merge, and we see that primordial black hole merger. And you can go away and calculate in more detail the rate for this process. So if you just take randomly distributed primordial black holes, just scattered uniformly, I've written unclustered here with a little asterisk because I'll talk a little bit more about that towards the end of the talk. But you can calculate essentially the distribution of the size of the orbits, the semi-major axis, just from considering the typical separation of these primordial black holes. And then the angular momentum of the orbits, the eccentricity, that comes from talks from other primordial black holes nearby, and also from smooth density perturbations. Okay, and so you can calculate this distribution of the size and shape of the orbits, and you find that if you're interested in binaries which merge today, so these contours here are the estimated merger time of a particular binary, then what you want is a small binary which is also very, very eccentric. So these values here all correspond to an eccentricity which is very, very close to 1. Okay, and so you can look at, you can then convert this distribution of semi-major axis and eccentricity into a distribution of merger times, and therefore calculate the merger rate today. And so these lines show you the merger rate as a function of the fraction of primordial black holes, and you can compare that with this estimate of the black hole merger rate. I think this number comes from an estimate which was done immediately after this initial observation, and this bar has probably shrunk a little bit, but not by orders of magnitude. Okay, and so what this tells you is that if you want to be consistent between the observations by LIGO and the expectations from primordial black hole mergers, then you have to be solar mass primordial black holes have to be a subdominant contribution to dark matter in the universe. Okay, you would form too many binaries which would merge too often if you're up here. As you decrease this FPBH, then you form fewer and fewer binaries, and you're saved from this constraint, or you can match or at least not overshoot the LIGO bound. Okay, and so this is where the picture becomes a little bit more complicated, because if primordial black holes are subdominant, then that means that you need another contribution to the dark matter density in the universe. Okay, and so what you likely have, if this is the scenario that you're thinking of, is that you have some small population of primordial black holes in addition to some contribution from particle dark matter. And when you have this mixed kind of scenario, what happens is that these primordial black holes in the universe seed the formation of local dark matter halos. So as the universe becomes more and more dilute before matter radiation equality, dark matter starts to infall towards the black hole. Okay, as time goes on, the sphere of influence of this black hole grows, and the size and mass of this dark dress, this local dark matter halo, increases. And so by the time you get to matter radiation equality, you can have a mass of the halo which is roughly the same as the mass of the primordial black hole. And even into later and later times, this halo continues to grow. And it can have a very steep density profile, so it can be very dense towards the center. And the reason, I mean, there are a few reasons that these things are interesting. One reason for us at the moment would be that dynamical friction within the particle dark matter halo can exert a force on other black holes. Okay, so essentially a gravitational friction force of a black hole moving through this field of particles can change the dynamics of the system. So this is not about primordial black holes strictly, but we looked, this is also interesting in a slightly different context. So if you have intermediate mass black holes, which have this shroud of dark matter around them, and they're actually in a binary with some smaller object, then the dynamics of this smaller object can be affected as it orbits around. It can be affected by the dark matter halo. Okay, you get this dynamical friction force, which can cause the phase of your gravitational wave signal to shift compared to what you would expect if there was no dark matter there. Okay, so these dark dresses, these dark halos, can have an important impact on the dynamics of the system. But for us, coming back to the main point, we're interested in how these dark halos could affect the dynamics of primordial black hole binaries. Okay. In particular, as these binaries, as they go through a close passage, each primordial black hole passes through the dark dress of the other. And so what we did was we set up some simulations to study these orbits. So we can take a look at this animation. So each of these is a halo of dark matter particles, and at the center, which you'll see in a moment, there is a primordial black hole. Okay, so they undergo a close passage, and with each close passage, more and more dark matter gets stripped away. Okay, and so at the end, the link is up here if in case you want to take a look at these videos in more detail. But at the end, what you find is that the dark matter has been stripped away from these systems because of this sort of violent interaction, but also the orbit has shrunk substantially. So the initial orbit would have been way out here with a large semi-major axis, and now it's much smaller. Okay, and so the new picture that you should have in this kind of combined universe is that these black holes move away from each other under the Hubble flow. But as they do so, they grow these dark matter halos. They decouple, and then as they undergo these close encounters, they should eject a lot of this dark matter, but they should also change their binary properties. Okay, they should in particular shrink. It turns out that there are really two effects that happen when these things pass through their respective halos. One of them is that the binary shrinks. This is because you use up some of your energy in ejecting the dark matter particles, but the orbits also circularize. Okay. And this basically just comes from conservation of angular momentum. That because these are very, very eccentric orbits, you don't tend to exchange much angular momentum between the black hole and the dark matter halo. And so if you shrink this binary, then your only option to conserve angular momentum is also to make it more circular. Okay. And so there are kind of two effects at play here. You shrink the binary and you circularize. Now, shrinking the binary means decreasing A, so that would, in principle, decrease the merger time. Circularizing the binary would mean increasing J, okay, this angular momentum, dimensionless angular momentum parameter, which in principle would increase the merger time. So these two effects should, they go in opposite directions. And as it happens, the two effects almost cancel. Okay, there's a sort of funny coincidence that happens. And so the final merger time depends, is generally quite close to the initial merger time. There's just this ratio of the initial to final semi-major axis that we find. Okay, so what this does is gives us a prescription guided by the n-body simulations to map from some initial distribution of orbits onto some final distribution of orbits once the dark matter halos have been ejected. Okay, so that's there. And so now we can return to this plot showing the merger rate as a function of the primordial black hole fraction. So the dashed lines were this somewhat incomplete picture that we had before of a universe filled only with primordial black holes. And then these solid lines now are trying to be a bit more careful and including, where it's relevant, this population of particle dark matter and the halos which form around the primordial black holes. Okay, but because, as we said, this merger time isn't drastically affected, it means that the merger rate is also not drastically affected. And so actually the merger rate increases perhaps by a factor of 2 or so, okay, which in the end will strengthen the constraints, though not drastically. And so what this allows us to do, comparing the LIGO constraint on the merger rate. So I think this is actually just the 01, the first observational campaign constraint on the merger rate. We can compare that with this merger rate that we've calculated, trying to be careful and self-consistent about the influence of these dark matter halos. We can actually set a constraint on this fraction, okay? And so this reaches down to about 1 part in 1,000 for primordial black holes with a mass of about 100 solar masses, okay? And so this is, I mean, this was kind of the end of one part of the story, and then the next part of the story is, okay, so what are the prospects for actually discovering primordial black holes? We can constrain them in this way, but what are the prospects for some kind of discovery? And so we went one step further and we said, what are the possible channels, possible ways you could make this discovery? So one of them is with a gravitational wave detection. The way that you would tell that you for sure had that you had primordial black holes in that case would be to detect a subsolar mass black hole. Okay, because then you know that this can't be formed through conventional astrophysical channels. You can't produce a black hole which is that light as the end product of stellar evolution, and so you would know that you're dealing with primordial black holes. And so you can then reverse the argument that we had for the constraints. And given a number of observed candidates, we estimated what the constraint would be on the primordial black hole fraction, or what the estimated value of the primordial black hole fraction would be if you made this observation. Okay, and so if it turns out that LIGO's third observational run has seen a single subsolar mass primordial black hole, then we will probably know that PBHs make up something like 1% of the dark matter in the universe. Okay, another possibility is the detection of gravitational waves from a merger at very high redshift. Okay, well, depends what you mean by very high, but in this case, if you observed a merger at a redshift above z equals 40, the conventional wisdom, astrophysical models tells you it's very hard to produce a 10 solar mass black hole at such a high redshift. You simply don't have enough time in the process of stellar evolution to produce the black holes and then form them into a binary and then have them merge. Okay, and so with sufficiently high redshift observations, which should be possible with the Einstein telescope, if you did detect something at such a high redshift, then you would be able to detect a very small subdominant population of primordial black holes. Just one high redshift event there would correspond to a value of something like 10 to the minus 5, 10 to the minus 4 PBH fraction. Okay, and I'm cutting off each of these lines at the maximum possible number of candidates which would be allowed by current constraints. Okay, so as we saw in one of the previous plots, if you're looking at light subsolar mass black holes, they're constrained to be 10% or less of the dark matter. Okay, and so we cut off this constraint. We cut off the projections at that value. Okay, last possibility is the detection of accreting galactic primordial black holes. Okay, so primordial black holes at the center of the Milky Way, which are accreting gas and then emitting radio waves and X-rays. Okay, in this case, it would be a little bit more tricky to say, you know, I have a primordial black hole just from one observation. We would be talking more about a population study to understand the distribution of these sources. But we think that that's possible with the square kilometer array radio observations in the late 2020s. Okay, and so in this case, you could really observe something really, really small, you know, some very small fraction. And so the other consequence of these dark dresses, these dark halos around primordial black holes, is that because they're so dense, they're also an incredible source of dark matter annihilation. Okay. So as the density rises towards the center of these objects, the density becomes so high that annihilation becomes incredibly efficient. And so these things should act as bright gamma ray sources. And in fact, the annihilation should be so efficient that towards the center, you should have essentially a plateau in the density of dark matter. It should be annihilating away very quickly. So it should flatten out. Okay. And so what you can do is you can say, if I observe a particular number of primordial black hole candidates, that tells me how many primordial black holes there should be in the universe. I can infer what the fraction of primordial black holes in the universe should be. And from that, I should be able to infer how many primordial black holes should be in the Milky Way, but also how many should be broadly in the universe, which should be surrounded by these dark matter halos, which, if they're some kind of wimpy dark matter, should be annihilating to gamma rays. Okay, so you can then go away and look at how many point sources in the Milky Way would be compatible with that kind of halo, but also what kind of diffuse emission, looking back out to high redshift, would be compatible with gamma rays from dark matter annihilation. Okay, so let's return now to this picture, which we kind of had towards the beginning of the talk, which was looking at the annihilation cross-section for this dark matter particle against the mass of the particle. Okay, and the thermal relic line, which is the sort of typical value that you need to give you the correct relic abundance for dark matter, is way up here, and we're looking at very low cross sections, annihilation cross sections. Okay, and so what we do is we say, if I observe one subsolar mass black hole during the 03 run of LIGO, or we also look at the most optimistic possibility, you know, the possibility which is consistent with current bounds on the primordial black hole fraction. So we could, in principle, observe 80 subsolar mass black holes with LIGO 03 and not exceed the current bounds. that observation tells us how many primordial black holes we should have in the Milky Way, which tells us how many bright gamma ray sources we should have in the Milky Way. And the fact that we don't have that many bright gamma ray sources allows us to constrain the annihilation cross-section for WIMP dark matter. Okay, and so in this case, the fraction of dark matter in primordial black holes would be so high if we observed just one subsolar mass merger that we would expect a huge number of bright gamma ray sources, okay, which means we can place incredibly strong constraints on this annihilation cross-section. And this is where we come back to werewolves, because werewolves are hard to kill, but they can be killed, as everyone knows, with silver bullets. Okay, and these dark matter models, these WIMP models, so this shaded region here is the MSSM, which I showed you earlier. There's also this scalar singlet model. These models keep stretching down to very low values of the cross-section. And no matter how many indirect detection bounds you place here, it's very hard to press down into this region and to really get rid of these models in a convincing way. Okay. But if you observed just a small number of these primordial black holes, okay, from LIGO-03 or from radio observations with SKA, or a high redshift with Einstein telescope, you would be able to set incredibly strong bounds, not just on thermal relic dark matter, but also on some subdominant particle dark matter models. And in a lot of cases, eat away at almost this entire allowed parameter space for these models of new physics at the weak scale. Okay, and so we called this paper Primordial Black Holes as Silver Bullets for New Physics at the Weak Scale, because it had been appreciated that this kind of thermal dark matter particle was incompatible with primordial black holes. That had been appreciated previously, but I think something which hadn't been appreciated was just how far down in cross-section you could go just if you observed a small number of primordial black holes in the coming years. Okay, so it's an incredibly interesting thing. I think it motivates, it's one of the motivations for looking for primordial black holes, because it's just completely incompatible with other dark matter candidates. Okay, and so coming back to this gravitational wave picture of dark matter searches, we were focusing here on primordial black hole mergers, which just tells us something about heavy dark matter. But actually, because of this interplay between WIMPs and PBHs, it actually can tell us something about a much broader range of candidate masses, okay, essentially overlapping with this indirect detection region here. So there are a couple of ways that we want to extend some of these calculations. For example, the impact of these dark dresses. We actually just studied it in the case of a monochromatic mass function, so where each of the primordial black holes has the same mass. But it's interesting to look at how this would change for extended mass functions, in particular because this smaller black hole is unlikely to strip. It's less likely to completely strip away the dark matter halo of the larger black hole. And so that halo can persist and perhaps have a larger dynamical effect. That's going to be in collaboration with a PhD student here in Santander, Katiba Jangra. And then kind of looking forward to another way of deciding whether you have primordial black holes or astrophysical black holes. We want to look at whether or not you can use the merger rate as a function of redshift to distinguish between astrophysical black holes, which, as I said, the rate of mergers should drop very steeply as a function of Z, just because you don't have time to produce these binaries. Whereas for primordial black holes, the drop as a function of Z is not quite so steep. So this is in collaboration with a master's student and some postdocs in Madrid. Okay. So that's the kind of the main story that I wanted to tell, and then the last 10 minutes or so, if I have time, I'm going to talk about some ideas that have come up in the past 6 months. One of the ideas I won't be covering is some controversy over the choice of metric that you use to define the growing mass of the primordial black hole in the early universe, which I'm sure some members of the audience were on these papers and can have this argument without me. But instead, what I'm going to talk about was a big red asterisk which appeared earlier in the talk, which was around the clustering of primordial black holes. Okay, so the picture that I was describing early on was this idea of a black hole, a primordial black hole binary, which forms in the early universe and then manages to persist unperturbed all the way to today. And the problem is that that kind of assumes that these primordial black holes aren't clustered in any way. And it's possible to enhance the clustering of primordial black holes if you have a particular shape of the inflationary fluctuations. You can enhance power on different scales. But even if you initially seed these primordial black holes uniformly distributed, so essentially just Poisson sampling, putting these guys in different places in the universe, because they're so heavy, they will start to cluster at late times. Okay, and so by the time you get down to Z of 100, Z of 30, sort of the time that we start to worry about structure formation in cold dark matter, you will have clusters of primordial black holes. Okay, and depending on the fraction of primordial black holes that you have in the universe, the typical size of these clusters changes. And this idea has actually been around. It's been known for 10, 15, 20 years. Okay. And so and this isn't just a sort of a theoretical idea. You can actually go and do simulations. And so this is results from an incredible paper by Inman and Ali Hamoud, where they simulate what they call lambda PBH cosmology. So they have simulations including primordial black holes and particle dark matter. Okay, so this panel on the left shows the density contrast in a universe which contains just a small fraction of primordial black holes. Okay, so this purple region shows the density contrast. And then on the right-hand side, you have essentially this density contrast in a universe which only contains primordial black holes. And each of the white dots in here is a primordial black hole. And as you can see, the structure which is formed is much more rich. You formed clusters and a much denser structure, even at a redshift of 99. Okay, and you can go away and calculate you can estimate analytically the typical size of these halos, how many halos of primordial black holes there should be, halos or clusters, how many primordial black holes that there should be in each cluster. Okay, and the simulations seem to agree pretty well with this Epstein. The dashed lines are this analytic estimate for how many of these clustered halos you should form if you just have an initially Poisson distributed black hole field. Okay, and so if you're looking at something like if you're looking at a completely primordial black hole dominated universe, then you should have typical clusters on the size of 100 or 1,000 primordial black holes, say. Okay, it turns out that these primordial black holes are actually, they form, but then at some later time they evaporate. They essentially are not stable in the long term. Two-body interactions tend to relax them and kick out primordial black holes, and eventually these things should evaporate. And the reason that we would be concerned about this is that if you're in this dense environment, if your binary finds its way into this dense environment, which it very likely would, then it's quite likely to be perturbed by third bodies, by other primordial black holes which are nearby. Okay, and so we have to try and think of a way to deal with that, to estimate the impact. Okay, and so in a couple of papers here, the authors try to come up with a way of estimating the size of this disruption effect. And so one thing you can do is you can say that the fraction of binaries which have not been perturbed is essentially the fraction of binaries which are in clusters which survive to today. Okay, if a cluster evaporates or collapses before today, it means that it must at some point have had a very dense core. It must have been a very disruptive environment for these binaries. So if you only include binaries which are in clusters which didn't collapse or didn't evaporate, then that gives you some sense of what fraction of binaries should have survived until today unperturbed. Okay, so that's what this NP is, not perturbed. Now you can calculate this fraction as a function of redshift. You can calculate this just based on the typical sizes of these clusters and how long you expect it to take for them to be disrupted. Okay, and what you can do then is you can essentially apply this suppression factor. So you can go from this merger rate, which we were talking about before, and apply this suppression, which you say, well, a lot of these things lived in clusters which actually collapsed or were very disruptive. So it's unlikely that they survived in the way that we're thinking of. And so you expect some correction to the bounds that you get on primordial black hole dark matter. Okay, so this is the sort of typical sensitivity you expect from O2, the second observational run of LIGO. And then if you include these perturbations, you see that you get a substantial change in the constraints as your bound gets closer and closer to 1. So as these clusters become more important because you have more primordial black holes, then the bounds can weaken substantially. Okay, and it would be nice to go beyond these kind of conservative analytic estimates, and so a number of people have started doing simulations. So, for example, this paper up here is essentially a cosmological simulation, including only primordial black holes, looking at how they form binaries, how they form clusters, starting at some relatively high redshift and trying to trace this all the way down to today. Okay, and this shows the number of surviving primordial black hole binaries. So if you have a small fraction of primordial black holes in the universe, then you just have a relatively small number of binaries, which is fine. And then if you have a large fraction of primordial black holes, you get this initial increase as these objects form binaries. Then those binaries get disrupted at late times, and so you can have a substantial decrease in the number of binaries and therefore in the merger rate. So unfortunately, these simulations couldn't trace the merger rate down to low redshift, certainly not for these kind of very dense primordial black hole environments. But they can almost reach low enough redshifts for very subdominant primordial black holes, so 10 to the minus 3, 10 to the minus 4. Okay. And what we find is that actually these simulation results seem to match up pretty well with the analytic estimates that I was showing you before. Okay, so this in some sense should give us confidence, although it's tricky because these simulations don't reach down to a redshift of 1 or 0, but they also are not yet able to resolve these late time mergers in universes which are quite close to primordial black hole dominated, where this clustering effect could be the most relevant. Okay, a different set of simulations this time. In this case, it's not a cosmological simulation, but it's a simulation of individual primordial black hole clusters. okay, isolated clusters, each one with 1,000 primordial black holes, okay, without any kind of gravitational wave emission or any kind of merging by binaries over a long time. And what the authors of this paper did was they studied the ejection of primordial black holes from these clusters, but also studied mergers that come from hyperbolic orbits. So essentially primordial black holes which pass near enough to each other to be immediately captured and then merge through gravitational wave emission. Okay, and if you scale these results up, there's sort of results for one cluster up to kind of the universe and what we should see nearby, you find that the merger rate for a primordial black hole dominated universe should be something like 1,000 per gigaparsec cube per year, which is a factor of 10 larger than the observed LIGO rate. Okay. So this is suggesting, these simulations seem to suggest that this evaporation shouldn't really be a problem. This disruption due to clusters shouldn't really be a problem. You should still have a very large merger rate. Okay, and in the last few minutes, these simulations by Adamczyk look instead at three-body encounters in particularly large clusters, so clusters of 1,000 or so primordial black holes. Okay, so what he does is he takes a binary and then perturbs it with a third primordial black hole. Okay, and you get these crazy three-body interactions, and the properties of the binaries can change drastically. Okay, so you get one of these things ejected, or you just get some perturbation. But what you find is that if you look at all of these binaries, if you look at the merger time initially, and then you look at the merger time after they've been perturbed by this third body, you find that everything is shifting upwards. Okay, everything is going above this this line. So what happens is that these three-body encounters in dense clusters should massively increase the merger time, massively decrease the rate of mergers of these binaries that we see today. And so what this means is, and what Adamczyk argues in one of these papers, is that the merger rate of binaries which form in the early universe should be completely negligible. But instead, what should dominate is actually direct mergers. Like I said in the previous simulations, what should end up dominating is primordial black holes which essentially come very close to each other, close enough on hyperbolic orbits that they emit gravitational waves and merge very quickly. Okay, and here the estimated rate from these calculations matches roughly the LIGO result. Okay, and so this picture, in some sense, is a bit of a mess. It's possible that this region here could be allowed due to clustering because you form these disruptive clusters at large PBH fractions. But one thing is for sure, that the picture that I presented early on in the talk is much more complicated, or the real picture is much more complicated. So as well as these late universe binaries, these early universe binaries which can form, you can also perhaps have these direct mergers which are relevant because of clustering. I think this whole picture is still evolving, but my feeling is that we need some kind of multi-scale simulations which capture all of the physics going on from the early universe to these late time clustering problems. And that's not a simple task. So I showed you that we can perhaps come up with constraints on primordial black holes, although we have to worry a little bit about dark matter which can gather around them. Once we detect primordial black holes, if we detect primordial black holes, then that can also have strong implications for particle dark matter, which has collected around and could tell us a huge amount about new physics at the weak scale. But really, if we want to do some kind of careful estimate, some inference about the primordial black hole fraction, once we make an observation, I think there's still a lot of work to do, and I think that the field is still in a state of flux. Thank you very much.
Thanks, Bradley. That was really interesting. If anyone has any questions that they're itching to ask, then do just jump in. But if not, I will ask the customary first question. I have a slightly technical, well, not really that technical, but it is a sort of very minor question, which is with your silver bullet plot, why were you constraining the WIMP fraction to the 4th power? That sort of took me by surprise a bit.
Yeah, so usually these constraints go like f squared because you're interested in a density squared. So it turns out that the annihilation rate depends in a complicated way on this WIMP density. So essentially because you form a plateau in the in this inner region, you basically annihilate away the particles. This means that the annihilation rate doesn't depend in such a simple way on the fraction of dark matter that you have. It's essentially, yeah, in the standard calculation, you can just say that the rate of annihilation scales as rho squared, whereas it's a little more complicated because this central density is also controlled by the cross section. And so there's a slightly more complicated dependence there. By the exact origin of why it's f to the 4th rather than f squared just comes out in the scaling of these things.
Any other questions? Please feel free to ask. If not, I think I'm still getting my head around this Yadamzik result, which was showing that so when you say the merge rate is dominated by these direct mergers, does this mean that they also okay, so there's he's also somehow suppressing the merger rate at early times as well as enhancing it at late times. Is that right? Because you need to sort of somehow lift up the LIGO bounds whilst also providing this additional source of mergers.
So first of all, I'm still getting my head around the Yadamzik result, but essentially, as far as I understand, you essentially get rid of the rate from early universe binaries by saying that as soon as these things enter dense clusters, and his argument is that almost all of them do, as soon as they enter dense clusters, they undergo these 3-body interactions, which completely changes the merger rate. Okay, so you essentially have almost no surviving binaries which have the correct merger time.
Yeah. Okay.
Yeah, and then what you have is just a dense environment full of primordial black holes, which are in a great configuration to essentially hit each other, I don't know, head on, essentially, just by chance merging because they happen to get close enough together. And when you put the numbers in, it turns out that matches pretty closely with the LIGO constraint on the merger rate.
So I haven't looked in this in detail, but so he looked at basically just a bunch of 3-body simulations with a certain number of primordial black holes in them. So this one is 1,300. Is that
so? As far as I understand it, he envisages a cluster of primordial black holes, and then you can you can look at that system and you can sample 3-body encounters. You can say, if I have a binary, what's the relative speed and the impact parameter for another body getting nearby. Okay, and so he basically samples these 3-body encounters, and for each one actually runs a simulation to see how that 3-body encounter would affect the parameters of the initial binary. Okay, so essentially his argument is that you don't need to simulate the whole thing. You just look at an ensemble of different encounters, and you see how that ensemble of encounters changes the merger rate. I mean, I'm not 100% convinced by that argument.
Yeah, I mean, isn't the 3-body problem is like one of the famously chaotic systems? It's easy, that straightforward to derive something from an ensemble. I don't know.
Yeah, this is part of the problem, that there's physics on like lots of scales, and so you've got binaries that you're trying to evolve, but then you've also got three-body encounters happening. But these 3-body encounters are also happening in a dense cluster, and so it's not clear how much you can call them 3-body encounters.
Yeah,
and these things tend to be dense enough that they're hard to simulate carefully.
So
I maybe have a comment. It's Franciolini. So thanks for the nice talk. Maybe just one comment regarding the clustering, since you mentioned the paper we had with Riotto, Dejac, and De Luca. It seems that one is able to recover the results by the n-body simulation of Aliemut and Inman in an analytical way. So what we did, we just repeated the result that you cited by Vasconen, so the estimate for the merger rate with the suppression factor. And it seems also accounting for this correction by clustering. The results stand, so they're quite solid. So it seems also accounting for clustering, you're not able to evade the constraint.
Okay. So you're saying that I think you're one of the papers.
Yeah, the latter one. Yeah, the latter you're citing. Yeah, basically we recovered the result by Vasconen and Vermeij that you're citing, but accounting for clustering.
Okay.
So that's just
okay,
a comment. Maybe another comment in the plot that you show about the constraints on the LIGO band. Maybe there are some relevant constraints from Serpico that appear this year that are probably more stringent than the one that you are citing from CMB acquisition constraint.
Yes. So in here somewhere, I think probably they should probably be much steeper down here. I think I probably took this plot from the original paper, whereas the bounds and the bounds that we used in the review should be more up to date. Sorry about that. But no, your comment about this merger rate, including the clustering, is, I mean, it's interesting because there seem to be different schools of thought, or there doesn't seem to be a consensus forming about what the merger rate for primordial black holes should be if you have f equals 1. So to my understanding, you sort of do an update of these bounds, which I'm showing here from Vasconen and Vermeij, but they don't seem to match up with what we were just discussing. For example, these simulations from Yadamzik. So I'm just saying it's a complicated and confusing situation.
Sure, but yeah, if I can just add something, they're not necessarily in tension. I mean, the Yadamzik simulation, they he simulated a very specific environment. And in our computation, we agree that those environments with these numbers of elements in the cluster are indeed reducing the merger rate for those binaries in those environments. The problem is that you need to account, and this is also cited in the second paper, you need to account for the fraction of binaries that lives in those clusters that is simulated. That's probably the harder part, but also critically important. And it seems, that it's enough for like 1% or even a smaller fraction of binaries to be outside those clusters, and the merger rate still remains above the live observations. This is,
okay.
and I mean, the results are not necessarily in contrast with the G-Damsic simulation.
Okay. So you're saying that in addition, you have to account for binaries which don't enter these clusters, which survive outside. Okay, which can also have a contribution. Okay.
Yes.
Thanks.
This is my view. I mean, but of course, it's a very exciting topic.
No. I mean, I understand, and I think putting all of these different components and different contributions together is, it's a slightly tricky, sometimes complicated task.
Sure. Thanks.
Kieran, maybe we should stop